So for our first talk of the day, we have George Datseris talking about Julia Dynamics. So Julia Dynamics is a Julia package which recently won an award by SIAM, which is very good, I think. So if we could thank the speaker and you can start.
Thanks a lot. So my name is George Datseris. I am doing my PhD in physics. I work at the Max Planck Institute for Dynamics and Self-Organization. This is in Germany. So my PhD topic is about electron transport, both quantum and classical. But today I'm going to take a detour, and I'm going to talk about why I think, as a scientist, that Julia is the most suitable language I could use. That would be the first part. And the second part would be introducing this Julia Dynamics organization, show you what you can do with it and how we use Julia there. So I have to, of course, start with a huge disclaimer, because if you have such aggressive claims, people get very, very, very intense about it. So when I say most suitable, what do I mean by that? I mean the most developer-friendly most of the time, all right? I mean most performant most of the time. As we all know, there is no panacea, there is no one drug cures everything. Second disclaimer, what you will hear are my own opinions, all right? And finally, yes, I am aware that something that I will talk about can be done with other languages. All right. So, to start, here is a question. What does science need from code from a programming language? So when I'm given a question I want to answer using computers, these are the steps I will do. First, I have to think about how can I possibly answer this question using a programming language. This is step one. Step two is to actually implement my ideas in the code. Step three is to run the code. And step four is to read your results and visualize the results, preferably using the same language. And step five is to understand that your results are total nonsense because they are full of bugs, so you have to debug. And step six is to run the code a final time. So this is my workflow as a scientist. And what you notice is that from these 6 steps, only 2 are I let the code run, all right? The other 4 steps is me and the language working together interactively to solve a problem. This is why I think the most important requirement science has from a programming language is the performance of actually doing science, all right? The performance of giving an answer. And in my eyes, this cannot be done truly performantly without an interactive language, okay? Of course, science equals number crunching, so you need performance of computation. This is also a standard. And a third thing you need is source code that is concise, intuitive, easy to read, and easy to understand. Why? So that the person that wrote the code is not the only one that can use the code. That is why. The fourth requirement is that you want code that is very easy to share with other people and very easy to immediately start, to install it, to start it, and to replicate it. And finally, of course, you want something that is free and open sourced. So this is a list of really big requirements. However, since you are here, you probably all know already that Julia does fulfill each one of these requirements. And it is advertised as such. So it is a dynamic language. It is super performant. And most importantly, in my eyes, solves this age-old 2-language problem, which I consider a hyper-massive benefit from science. You never will have again to write in C and in Python and at the same time. So my talk assumes that this is basic knowledge. I assume everybody in the room knows this. And if the people watching on YouTube do not know this slide, then I can highly suggest watching this talk by Nick Eubank, where you can find in YouTube. So my talk will be pointing out something that I consider to be unspoken powers of Julia. Like, for example, that multiple dispatch and functional programming more often than not equate the scientific algorithmic thought. How Julia brings unprecedented productivity and clarity. And other stuff like, for example, sharing and using other people's code is super easy, and most importantly, understanding it's super easy. And as a random example, just look at a typical function from base, and you will see that you can actually understand the base of Julia without much of a problem. And this is super important because it removes black boxes. Now, let me give you some examples of syntax that I found really, really important in my work, one of which is, of course, Unicode. So this is an expression taken directly from my thesis. And the only symbol that is missing in my thesis is the asterisk. Everything else is actually the same. And on the right, I compare it with the same expression, but in Python. And yes, I am aware that you could use alpha in Python, but it turns out most Python users do not know this, so you actually will never see it in a Python code. Another example that I really love is custom infix operators. So what does this mean? This means that you take a Unicode symbol from a very, very big list, and you define a binary function on this symbol, and then you can use it as an infix operator, like this. So you might now say, come on, this is really specialized, no one will ever use it. So I disagree with you, and so do the people from quantum optics, where they define this Unicode symbol, which is the tensor product operator. And so you can write things like psi equals psi x tensor psi y, and this you would find typically in a quantum mechanics textbook, for example. So I use this. Last thing about syntax that I also really love is the broadcasting, also called dot fusion, which means, hey, you have a bunch of arrays, and you want to broadcast a function along the different dimensions. So the only thing you have to do is you put your dot here, and Julia takes care of everything. And of course, the important part is that this applies to user-defined functions as well, not only built-in stuff. So now let me give you some examples that brought me very, very big productivity. And so what I will do here is I will actually compare using Hydrogen and Python in the Atom editor with using Juno and Julia. So let's say I want to solve the life, the universe, and everything, and I assign the answer to this variable answer. So I type exactly this thing in Julia. I type it, I press Shift and Enter, and the answer pops up here. I know the answer, which is kind of important, and then I carry on doing my science with other stuff. So I write exactly the same thing in Python using Hydrogen. I press Shift and Enter, and I don't see anything. So then I type answer by itself. I press Shift and Enter. I see the answer. Then I delete the sole answer by itself because it doesn't make sense to just have it in your code, and I carry on. So this is for me important. You might say this is something trivial, come on, it's like takes you 1 second. That's true, I agree with this. But what if I do this thing 1,000,000 times in my life? Because I can guarantee you I will do this 1,000,000 times in my life as a scientist. So this really adds up. This adds up. Another amazing thing is that functions that mutate stuff end with an exclamation mark. And this is not even forced, it's just a convention that everybody uses. But this is so convenient because you know, if you see this thing, okay, I know this will change. I don't have to search about it. I don't have to go to the source code. This will change. It's fine. Let me point out why I think Julia also stands for reproducible science with this new package manager and the new project setup. Because the way it works is you have your project, you add a package that you want to use, and it is automatically added in the dependency list. So then you send your project, and now by project I mean your source code and the .toml files. You send these to your colleague, and your colleague does instantiate. And then suddenly, whatever has run in your computer runs in their computer. So this immediately allows you to reproduce the results. And because Julia is Julia, and almost all code is written in Julia, I imagine that everything will be very, very easy to install across different machines, different computers. In addition, this has the possibility of having different package versions for different projects, which is of course great. And talking about robustness, I just want to quickly point out the new implementation of missing we have, and I encourage you to read the Julia blog post on this, because not only it works with all major types, but it's also safe, and this is very important. All right, so that was the first part of my talk. In the second part, I want to introduce this Julia Dynamics organization and show you 5 aspects that highlight using Julia in scientific computing. So the first package we have is this DynamicalBilliards.jl. And billiards are very useful systems that have been used in science from simulating gases to nano devices. And what it is you have a particle inside a domain, and the particle is propagating by colliding with the obstacles. All right? So before I go into the features of this, let me say that I'm super proud that some people have already used it in research, and in fact, Diego and David have somehow contributed there, and they made periodic billiards with it. So the features are this, what you see here. So you can construct arbitrary billiards from obstacles. You can have, for example, boundary maps or periodic billiards. So these are standard stuff that you would find in other billiard software packages with other languages. However, we do have quite a long list of unique features that I couldn't find anywhere online, like, for example, ray splitting or Lyapunov exponents. So of course, I'm not going into details. You're welcome to see the documentation, because one of our great features is that we are very well documented. So this is what you can do with it. And let me now give you an example of how we use Julia. So to simulate a billiard, you have the following problem. You have your particle somewhere, and you want to find the next collision of this particle. So the way you do this is you compute the collision time with all obstacles. So by obstacles, I mean these walls or this disk. These are the obstacles. You compute the collision time with all of them, and to find the next collision, you simply find the minimum time. So you find the minimum time and the obstacle it corresponds there, and then you say, okay, I found it. Now I will propagate my particle for this time. So in this example, I would go from here to here. Okay. Then I do a specular reflection of the boundary, and that's it. That's the algorithm to simulate a billiard. Then you just repeat as much as you want. So that is super simple, but what is clear is that I need some kind of function that computes collision times. And because this is the most basic thing, it will affect the design of the entire library. So if I was a Python user, I would say, is this function a method of the particle class? Is it a method of the obstacle class? Scientifically, this makes no sense, because a collision time is a process independent of classes, independent of data, independent of anything. And Julia allows you to keep it this way. Everything is independent. You have the collision time, which is a function. It exists by itself, and you define methods on the function based on the type of entities you have. All right? So this is how we do it. And to give you one more example of clarity, so here I compared the algorithm with the actual function that does this. And of course, as you can see, I call a different function in each line. So you might be saying this is not clear because you call different functions. But I can guarantee you that each one of these functions is actually 10 lines of code. So indeed, you can keep everything very, very short and concise. Moving on, scientists always ask about performance. It doesn't matter if they need 12 months to write code. If it's fast, this is the only thing they care about. So here I'm just answering these scientists, and I'm telling you that it is fast. So what I do is I benchmark how much time it takes to propagate a particle for one collision. So if you have a straight propagation, so like straight lines, this is 50 nanoseconds. And if you have a magnetic propagation where the particle moves as a circle, this is 300 nanoseconds. And this is very fast because typically what you want to do in billiard applications is evolve 1,000 particles for 1,000 collisions. And you would have to parallelize this, but now this runs on my laptop instantly. All right, so that was the first package of our organization. The second one is this one called DynamicalSystems.jl, which is actually many packages. And it has a lot of different features, but of course, due to time constraints, I cannot go into detail. I will simply tell you that there is a YouTube video on the Julia Lang channel where I overview all of these things. So in this talk, I will focus on the Lyapunov exponents only. And before I go in, let me mention what Yanis has already mentioned. So we recently won the SIAM contest for software about dynamical systems. So that was very cool, I think. And to start my introduction, I first have to tell what is a dynamical system, just for consistency. So it is very simple. It is simply a rule of how quantities evolve in time and a state to be evolved. This is a dynamical system. So in my case, they come in two flavors. They can be maps, which is what you see here, where time is a discrete quantity. So as I evolve the system, you see the state of the system jumps discretely from point to point. Dynamical systems can also be ODEs or set of ODEs. And what I show here is, for example, the Lorentz system. And as you can see, the state is flowing continuously as time progresses. Okay? Now, in DynamicalSystems.jl, we deal a lot with chaotic systems. These kind of systems, for example, the weather is one of them. And in these systems, initial conditions that are very close nearby start to separate exponentially. All right? So to demonstrate, by the way, the Lorentz system is a simplification of a weather model. So what I have here is I have two initial conditions very, very, very close. And I evolve the system in time. All right? And what you see is that as the system is evolving, the two conditions start to separate and separate and separate. And after some time, they are completely separated. By the way, this is exactly the reason where it starts raining and the forecast said, oh, it's going to be sunny. So next time it happens, don't complain because it's like a fundamental scientific reason, not the weather guys hate you or something. So how do you quantify it? You quantify it with the Lyapunov exponents. So these things quantify how fast these initially nearby states separate. All right? This is what they do. And what I'm going to do now is actually tell you how to compute them. This is important for later on. So the first step to compute these exponents is to initialize some kind of integrator and some kind of deviation vectors. And because I will talk about this in more detail later, just don't think about this. You have some kind of magic integrator for now. And the algorithm is the following. You evolve your dynamical system, and you evolve these deviation vectors simultaneously for some time delta t. And then you perform a QR decomposition on the matrix that has as columns these deviation vectors. You add into some summands the logarithm of the absolute value of the diagonal of the R matrix, and then you replace these k vectors, these deviation vectors with the columns of the Q matrix. That's the algorithm. You repeat it as many times you want. And then you simply divide with the total time span. You divide your summands with the total time span, and this is the Lyapunov exponents. What I show you here is the implementation we have in DynamicalSystems.jl. This is the full code minor modulo some minor details. And what I want to say that these 30 lines of code are called for any system, discrete, continuous, big, small, doesn't matter. It's the same piece of code. And on the left, you have a function that does the setup. It initializes the integrator. Let's not care about this for now. What I really want to focus is that on the left, I have the algorithm that I have been taught in university, and on the right, I have the code. And what I really want to point out is that you have a one-to-one code correspondence, a one-to-one correspondence between code and algorithm. So as you can see, each line of this algorithm corresponds to a single line of code and vice versa. So why do I think this is super important? So I have taken many classes in nonlinear dynamics, and I can tell you, you cannot study them without a computer, all right? This is very important. However, in all of these classes I have taken, nobody have ever shown me code, ever. So I was wondering, why would nobody show code? And the answer is simple. Well, code is complicated, you have to explain it, and code is very, very large. So that's the main concern. So I believe Julia can change this. I believe Julia can change physics education, because now you don't have to show this. You can just show this. And I think this is really important. So, of course, once again, some scientists, whenever you present them code, it doesn't matter the benefits, they care about speed, so you always have to show speed. So here I show that this Lyapunov exponent computation function is performant. So for example, the full computation of the Lyapunov spectrum of a discrete system takes around, let's say, 300 microseconds on my laptop, not on any computer, and without any parallelization. But what you care about in these applications, you care that you want to do a parameter scan. So you want to compute, like, let's say, 100 exponents for 100 different parameters. So what I do here is I take advantage of the interface we have and write a parameter scan function. So the function scans and uses a continuous system in this case. So continuous systems are around 3 orders of magnitude slower for discrete for obvious reasons. And so to scan 100 parameters of let's say the Lorentz system, you need 1 second. Once again, typically these are applications that you run on a cluster or you parallelize, but once again here I have the result instantly on my laptop. So the final thing I want to point out is something I also found, I once again found amazing when developing these things, and this is how easy it is to manipulate functions. So let's go into this integrator thing once again that I mentioned. So this integrator, what does is very simple. On one part, it evolves the dynamical system normally. On the other part, you have these deviation vectors that I mentioned, and the way this works is you have to compute the Jacobian of the equations of motion, and then multiply the Jacobian with the deviation vector, and this gives you the rate of change. So you see you have two different evolutions that must happen in parallel. And for example, since of course we use differential equations.jl for continuous systems, we want to give a single function that does this. So how does this work? This is how it works. You have a function that says create tangent, that actually creates this combo, and you give the function the f, the equations of motion, and the Jacobian. Now what I want to point out that these things are functions themselves, all right? So in Julia, nobody thinks about this. Okay, of course I can pass functions as arguments, no problem, but this is not always the case. And then what I do is I create a new function that uses these two functions and return this new function. So all of this is so easy and straightforward, I never even had to consider how to do it. I just said, well, I just give the functions, but it's not always the case, right? So this is, I think, an excellent showcase of using Julia. So to summarize, so Julia has made my own workflow as a scientist massively more productive. And I think this can apply to other scientists as well, not only myself. And please keep in mind, this is totally unrelated with these packages I have developed. I do use Julia in my daily work. So talking about packages, I presented JuliaDynamics. Please check us out. I think we try to do some cool stuff there. And since I am actually on video, I have the opportunity to present that there is another organization coming, totally unrelated, but I just wanted to showcase it, so keep an eye out. So thank you for being here. I also want to thank some special people. Of course, Chris has helped me tremendously with differential equations and setting things up and like a bunch of stuff. But also I want to thank these two amazing students. So Lucas is a bachelor student that has done amazing work on the billiards package I presented, and Jonas is another bachelor student that has done amazing work on the Dynamical Systems framework. And of course, all of these people that have helped me in some way or another, and thank you very much for your attention. Thank you very much for your attention.
Thank you very much for a very interesting talk. Does anyone have any questions?
Hey, so first of all, thank you for the amazing talk and for the amazing package. So I have a bit of a critical question. So you presented Lyapunov exponent estimation as an example, which is, as far as I know, one of these very, very difficult things. There's a huge research field just about how can I estimate a Lyapunov function for a chaotic system, like Lorentz versus other typical examples.
Sorry, excuse me, did you say Lyapunov function or exponent?
Exponents.
Okay, sorry. Okay.
Yeah, yeah. And so what I wanted to know is, did you compare your results with these other packages? Because I think that would be very interesting because you showed, hey, it can be done very simply.
Yeah, so of course, we actually have a huge amount of unit tests. I actually compared my package with every published result I could find on simple chaotic systems, and of course I found agreement everywhere. So as far as I know, they are pretty robust, yeah.
Thank you. Just out of curiosity, I remember as an undergrad, David actually made me calculate the Feigenbaum exponents. Is that in your package? And that was really complicated.
Which exponents?
The Feigenbaum constants.
The Feigenbaum. This is very easy to do with our package, yes. Because we actually have a function that can produce the orbit diagram for you.
Okay.
So if you have the orbit diagram, then you just divide, do a division, and that's it.
Oh, okay, nice.
Does your package contain anything for analyzing stability of fixed points?
Yes, in some sense. So most of the time you can do stability analytically if you know the Jacobian. So that's why quite often you do not use the package. But if I were to use some numerical method, I would just use the Lyapunov exponents, or simply see how the deviation vectors scale around the fixed point. Sometimes you don't really have to do fancy stuff for this basic application of fixed point stability. But if you're talking about something different, which is bifurcation analysis, then no, you cannot do this with my package, but there is someone who is developing a package for Julia called bifurcations.jl. All right.
Any other questions?
So the particles are bouncing around in this billiards environment. Yep. It's a universe that's two-dimensional with borders and like circular objects and other objects. Do the particles interact with each other?
No, you cannot do particle interaction because, first of all, we consider them point particles. So there is no size, and we also don't have any kind of electric fields or anything like that. So everything is point-wise in the sense. So this system is not actually continuous in the sense. It is a map. It is discrete. If you go from collision to collision, there is no size on the points or electric fields.
Well, what does magnetic mean?
Magnetic means that if you consider that this particle is an electron, it has some charge, and therefore if you apply a perpendicular magnetic field, it goes in circles instead of lines. In fact, this you can see in our logo. In the Julia billiard, you see the trajectory is not actually a straight line. You see it is part of a circle. This is what I mean by magnetic. So this is how it's called in the literature.
Oh, okay. So it's just a curved path.
It is a path of a circle instead of a straight line, exactly.
Do we have any more questions?
Just adding to that question, how can you comment on how Julia syntax and Julia language is good for extending these models? Where, for instance, you move from a straight line particle to a curve. Let's say if you collide with the walls of the vessel, some of your gas particles can be absorbed, say 10% of them every collision. Is that easy to do in Julia?
Actually, we already have this. As you see, it happens here. You can do exactly what you said, the equivalent, by passing a probability function. So what you see here is when it collides with this red disk, I have given it a probability function based on the incidence angle. It can go in or it can go out. So this is already implemented, but I really want to touch on what you said because extendability is extremely easy with this multiple dispatch approach. When I was writing this package, I wanted to make a tutorial of how you can create your own class of obstacle, so a different kind of wall or circle. And it turned out I only had to extend 3 methods, one of which was a one-liner. So it's super extendable and super easy to do all this kind of stuff, like this phrase splitting especially. Yeah.
If there's no more questions, we can thank the speaker again.